actually not the probability, it's really the ratio. It's P of xj given y equals 1 divided by xj given y equals 0. This is the relative importance of a feature. So if this quantity is high, this means that that particular feature is associated more with N1. Or if I want to make it more, this quantity is the one that is the log R is the one that is similar to the weights. Yeah.
Sorry, I sort of missed the connection. Why is it that naive space does better with higher dimensionality?
Oh, there's no real reason. In high, the sort of a joke statement there is that in high dimensions, all problems are fit. In high enough dimensions, everything is linearly separable. Because in infinite dimensions, everything is linearly separable. So as the dimensionality increases, there is kind of more room to fit it here. Unfortunately, as the dimensionality increases, there's more room to overfit it. So that's the fact that it does well in higher dimensions is take it to the pitch and solve. It's almost like it's an empirical observation that has no basis in theory. It's just this idea that as the dimensionality increases, you have more space to be classified. That's pretty much it. We've encountered that idea more formally with VC dimensions, for example. As the dimensionality increases, your VC dimensionality grows, which means your classifiers become more expressive. Naive Bayes by itself is a rather weakly expressive system, so as the expressiveness of this increases, things get a little bit. That's pretty much the weak. Other questions? The other practical thing about the naive Bayes is that we are not going to see enough data to get good estimates of the probabilities. Now, keep in mind, how are we? What does training? I'm using the word generative. What does training mean for naive Bayes? We count the probability. We estimate the probability of a feature xj equals, let's say, it takes the value 1 for a label y equals 0 by counting number of times xj is 1 with the value 0 in the training set divided by the number of times y equals 0. So this is the probability that oh, that's not p, sorry. Counting the number of times xj is 1 with y 0 divided by counting the number of times y 0 gives us the probability that xj is 1 conditioned on y being 0. Now, suppose we never see this pair. We never, for example, in the example here, we never observe the temperature being cold when we play tennis. That means the numerator here, this quantity, becomes 0. Now, if the numerator is 0, that means the probability is 0. And the question is, should we treat the probabilities as 0? Now, I already kind of hinted of what will happen if probabilities are 0. What would happen if probabilities are 0?
The entire product becomes 0.
The entire product becomes 0, which means we will have the posterior probability becomes 0, which means that particular label will never get chosen. If a single one of these things becomes 0, the entire probability of y equals, if this quantity is 0, then p of y equals 0 given x will become 0. Because in expanding this quantity, one of the terms will be p of xj equals 1 given y is 0. If that is 0, the whole probability becomes 0, which means you will never ever pick y equals 0. So that seems like a bad idea. So making probability 0 is always a bad thing. So how do we get around it? Any thoughts about how? Yeah.
You just add like 1 to everything. Everything has like a baseline minuscule.
That's right. That's pretty much it. That's the answer. So the answer is, it's called smoothing. Instead of starting your counters at 0, you start all your counters at 1. That's the answer. Or instead of starting the counters at 1, you can start it at some small number instead of 1. Who said 1 is a number? I mean, Everyone says 1 is a number. Who said 1 is a special number? Maybe you can start your counter with some epsilon. In fact, this is what you will do in your homeworks. This idea of adding small fake counts so that you don't encounter any zeros at all is called smoothing. Smoothing is an extremely important thing when we have when we are learning Bayesian models. This is like the simplest kind of smoothing. There's a whole line of work on smoothing with Bayesian models, and there are lots of explanations. It might seem like this idea of adding 1 while starting your counters is a hack. If you don't like performing, doing these kinds of hacks, if you want to sleep better at night, you can convince yourself, it turns out, that this is exactly the same as using a certain prior over the probabilities. So then, if you're doing this sort of smoothing, you're actually doing maximum a posteriori learning with a particular prior. This version of smoothing is called Laplace smoothing. Like I said, there's a whole line of work on smoothing that it's a beast, and this is just like scratching the surface. Yeah, you can ask me later if you want to know more about smoothing. So this is the simplest thing that you'll do. You'll be doing this in your homework as well. Any questions? Someone playing a game there. That's a very cool sound.
So our choice of what this number is a hyperparameter.
That's exactly right. Your choice of the smoothing parameter is a hyperparameter. You have to be careful how you do your smoothing, because when you add an epsilon here, let's say this starts with epsilon, so really that becomes epsilon plus. Oh no. Epsilon plus this thing on the numerator. In the denominator, you can't just add an epsilon. You should say plus epsilon times some quantity here, the number of features or something like that. Why? Because every time you every time you increment the numerator once for one feature, the y equals 0 gets incremented for all the features. So you have to add epsilons for. So there's some sort of normalization stuff that you should be careful about. Your homework gives you some details about that. Other questions about smoothing? If not, I'm going to summarize the Bayes with, there's one more practical thing, which is everything that we do, everything that we've done so far pretends that we have discrete features. Maybe the features are zeros and ones, but nothing prevents us from using continuous features. All it is that you have a different probability distribution. When you have discrete features, we had Bernoulli trials, basically coin tosses. If your xj, if your feature xj is a real valued, takes real values, then the probability over xj should be some probability distribution that can support real values. A very common choice, for example, is the Gaussian distribution, normal distribution. So you could pretend that P of xj given y is a normal distribution. I say pretend, that seems to make it look like a hack. Let's say it's a modeling assumption. We assume that these distributions come from from a normal distribution. There is an exercise that says you can derive the when your features are. I've made it a homework. This is your bonus extra credit question for your homework. Like I said, this is not only for grad students, also you can try. Basically, working through the whole naive Bayes thing. Maybe this is the homework question, or maybe not. There's a naive Bayes question involving normal distributions. Anyway, try this out. This is a good exercise because one of the this kind of maximum likelihood estimation is that you will work through a lot of math, basically just symbol manipulation, and you will come to a conclusion which is easy to explain. If you come to an answer at the end of deriving maximum likelihood, that consider that there is some error in your math. So this is a very nice thing about maximum likelihood estimation for naive Bayes. Quick summary. What you need to know with the naive Bayes is you need to know what the naive Bayes assumption is. All features are conditionally independent given the label. It's an important thing. All features are independent given the label, not just independent. They are only conditionally independent. You need to understand what the maximum likelihood learning becomes for the naive Bayes distribution. You should be able to generalize this to real valued features, like the thing that I just mentioned. You should know how to predict using naive Bayes. That's just map prediction. There are a few caveats to keep in mind. An important one that's actionable is the fact that you need to smooth all your probabilities while training. You need to do that. I mean, there is absolutely no excuse for not smoothing your probabilities because you will get bad results. Because not all features will show up with all labels, and you will get zeros. The fact that the independence assumption may not be valid is something that you have already agreed to live with if you're using the naive Bayes classifier. So it's part of it's a given. Now, it's also important for you to know that the decision boundary for the naive Bayes classifier is linear. The reason it's important will come up when we get to logistic regression. Any questions about naive Bayes? Yeah.
Is there some sort of semi-naive Bayes classifier that's like I have mathematical guarantees?
No.
Just a heuristic we do that?
So when you say semi-naive Bayes, you want to kind of relax this assumption, right?
Yeah, like you can embed certain conditional probabilities.
Right. Once you start doing that, you are now opening up the doors to all Bayesian networks. Because you need to start thinking about causality between you basically get to more complex Bayesian networks. They exist. You need to start thinking about how to model. It becomes more complicated. All right. So now let's go to a quick sort of a higher level point without talking, which is not going to be, we're going to talk about specific algorithms, but I want to kind of introduce this difference between generative and discriminative learning. The reason I'm bringing it up now is because so far we have not seen any generative models except for the naive Bayes. Naive Bayes is the first generative model we've encountered so in this entire semester. And generative modeling is a massive part of machine learning that we are again only scratching the surface. For most of the semester, we assume that we have a fixed distribution over the inputs, maybe the fixed distribution over input cross output. And our goal is given a certain data set, which is drawn from this distribution. There are some slightly different ways in which you can phrase that question, and you should think about the question in the box later. So, given a data set drawn from this distribution, the goal of learning is to identify a hypothesis space, find a loss function, find a classifier that minimizes loss. This is the framework of learning as loss minimization. Even though we didn't explicitly instantiate it this way for perceptron, turns out perceptron is also in the same family, and you can derive a whole bunch of learning algorithms. And the guarantee that comes along with this sort of learning is that if you find an observation and a hypothesis, I say an algorithm, a hypothesis that minimizes loss, then with high probability, this hypothesis will do reasonably well in the future. The bottom line, really, is that we are approximating a function from inputs to outputs. In particular, more importantly, we are learning how to directly make predictions. We don't care about how the data looks. We don't care about how the inputs look. We just want to learn a function that converts inputs to outputs. We look at many examples. We find regularities in the prediction part of the data, namely interactions between the x's and the y's, and we construct a prediction policy. Any assumptions that we may have in the in this process could be baked into assumptions about the hypothesis class and also maybe assumptions about the loss function. We can estimate the function that matches inputs to outputs, or more generally, we could estimate a probability that converts that predicts what's the probability for each label, or some sort of a score for each label. These classes of models, pretty much everything that we've seen, these classes of models are called discriminative models. We directly learn is instead of directly learning what the prediction rule is, we can model how the data is generated, how the instances are generated, and how the instances are labeled. And this is equivalent to saying we learn P of x given y, that's the likelihood, and we learn the prior P of y. And at prediction time, we combine these two to form the posterior probability. So given these two, we can compute P of y given x. And using Bayes' rule, and we predict using by computing the posterior. We did this. This is what we did for naive Bayes. Naive Bayes is an example of a generative model. It's definitely different from all the other models that we encountered, because in all other models, we never ever care about this quantity here. We never care about P of x given y. We don't care about generating the data. All we care about is the prediction rule. In the naive Bayes model, in order to get to the prediction rule, namely P of y given x, we went through the Bayes rule to get P of x given y and P of y. So what that means is that we have, in order to define this model, we have in our minds an assumption about how the data was generated. It's called the generative story. For naive Bayes, the generative story looks like this. Each example has to be generated using a certain process. The process follows the following. First, we sample the label from the prior. We have P of y, a circle with y means this is the random variable. We press the button, we get a value of y. We sample the y. Now, we have a y, we go one feature at a time. Given y, we sample a value of the feature x1. So we press this button, we draw a random sample from this distribution. We do this many times, as many times as there are features, and then we end up with the features, and we have managed to sample all the features and the label, and this gives us our training example. This gives us not just our training example. We believe this is how all our data is generated. We never made such assumptions with when we were doing something like SVM and things like that. Here we are assuming that we have a story for how the entire data is constructed. This is like a very simple example for a generative story, but all generative models come with a generative story. They come with almost a mechanistic process for generating x, y. In particular, generating x. In all other examples that we saw, we never cared about how the x's are generated. In fact, we assume that there is some distribution over the x that we don't care about, that we don't even know about. There is a fixed but unknown distribution over the inputs. In the naive Bayes, we are actually explicitly modeling the input distribution. In generative models, we do that. So, quick kind of differences between the generative and the discriminative models. The big difference really is in generative models, we learn the joint distribution, P of x, y. In discriminative models, we explicitly only model the prediction rule. We only want to get a function that converts x's to y's. We don't care about how the x's themselves are distributed. We don't care, we don't know, all we assume is that there is some fixed distribution. What this really means is that in generative models, all the capacity of the models that we have, meaning the expressiveness of the models that we have, is spread out to both model how the inputs are distributed and how the outputs are converted, how the outputs are associated with the inputs. So there are two things that we are expecting the models to do, both the input distribution and the input-output interactions. In discriminative models, we are using the capacity of the model only to characterize how the output is constructed, given an input. We don't care about how the inputs are distributed. Popular examples of generative models include naive Bayes. Some of you may have heard of the hidden Markov model. Hidden Markov model is a generative model. In discriminative models, today discriminative models seem to be more popular. Oh, another big family of generative models are topic models. Some of you may have heard of topic models. Discriminative models seem to be more popular today. Doesn't mean they're better or anything, they just solve a different task, and today we seem to be focused on solving problems, creating applications with machine learning rather than just modeling data. So the popular discriminative models include logistic regression, which we will see right after this. A certain way of thinking also says that SVMs, perceptron, etc., are all discriminative models. We don't really ever characterize how P of X is what P of X looks like. Discriminative models are sometimes also called conditional models. There are many names for these things. All neural networks, for example, are discriminative models unless they are explicitly trying to generate data. So if you want a picture, imagine that you have some task where you have points that are clustered, clumped together in groups like this. So there's like this one group of red circles, there's another one here, and there's a decision boundary between the red and the blue dots. A discriminative model uses its capacity not just to identify what the separator looks like, but also to discover all these clumps of data. The capacity is used to characterize the fact that there is this cluster here that is separate from this cluster here, and then there's this line here, and then and maybe your application needs this, or maybe not. A generative model does a lot more using the parameters, or hopes to do a lot more using the parameters. A discriminative model directly models the decision boundary. It does not care that the points are distributed in this way or that way, which is why they are kind of better suited for if you only care about an application. If you only care about the decision rule, if you only want to convert inputs to outputs. Generative models tend to be useful if you are building sort of latent variable models where you don't have fully labeled data, so you need to sometimes hallucinate examples or hallucinate labels. And they tend to be extremely useful. The math works out better. Discriminative models tend to have an edge. These are all not statements that are formal, but just they tend to have an edge when it comes to applications where you only care about the decision boundary. Yeah. Mike?
No. So in the previous lecture, you mentioned that naive Bayes is a linear classifier, but it's a subset of
Yes.
So in that case, like, how does that relate to the capacity ratio? And how is it a subset of like single?
So if you want to think of the set of linear classifiers that you are exploring when you are using an naive-based classifier, it does not capture all linear classifiers. In fact, there's a very cool example of a certain data set which is linearly separable, but cannot be classified using the naive-based model. If there had been a homework 6, that would have been it. But I can maybe share that with you at some point. But there is a cool example of that kind, which means that there are certain linearly separable data sets which naive-based cannot characterize. But every naive-based decision boundary, so the generative models give you both the decision boundary and the distribution of the data. The decision boundary that naive-based has is a linear, has a linear surface. But the naive-based also captures all these extra clustering of the data. So does that answer your question?
Is it like a trade-off? Like how you use your capacity?
Yeah, that's exactly it. It's a trade-off of how you want to use your capacity. Do you want to use your capacity to only directly characterize the boundary, or to also characterize how the inputs are laid out? Sometimes you need to characterize the input distribution, because you want to kind of you don't have labeled data, so you might have to actually discover clusters in the data because you don't know what label it should have, but this other point near it has a label. So you might need to characterize the input distribution, and in such places generative models are useful.
So if there's like if you introduce a new red point, let's say that's not like in one of those groups, does that like make it more difficult for the generative?
That's right. If you introduce imagine your data is small and you never saw another cluster that was here. Suddenly your generative model looks really bad. The discriminative model doesn't care. It does not even know about this, because it only given a point, it just needs to make a prediction. That's right. Which is why If all you care about is the application, then I would recommend using discriminative. And this has been kind of borne out by the success of discriminative models lately. Most of the neural network successes that we hear about are discriminative models. Most of the machine learning successes that we hear about are discriminative models because we only hear about successes in terms of applications. We don't hear successful stories involving latent variables and such things because those are inherently harder problems as a result where you have to use discriminative models. But they are less successful because they are harder problems. Yes?
So I'm kind of struggling with this concept, but when you say discriminative models focus on just the application, what is exactly the alternative? Like, what's the goal that changes in generative about caring about the inputs? Like, what information does that give you?
Oh, it does not give you information. You are essentially, so, outside of all the storytelling parts of it, mathematically, the only difference between generative and discriminative models is are you learning P of x, y, or P of y conditioned on x. Now, if I'm learning P of x, y, that means you're usually this boils down into learning P of x given y and P of y separately. Whereas here, you just learn P of y given x. Now, usually what that means is that using the top term there, P of x given y, I could, for example, say, imagine that you learned a generative model for email classification, naive Bayes, let's say, versus SVM. With an SVM or a logistic regression, what you could say is, given an email, is it spam or not? With a generative model, you could still say that because you apply the Bayes rule to get the posterior, and you can say whether an email is spam or not. But you could do a lot more. You could do things like, here, I believe that my next email is going to be a spam email. Generate a spam email for me because I can sample from P of x given y. So you have the ability to generate inputs conditioned on labels. You can't do that with the discriminative model. Think of an SVM. You cannot create an x given that the label is +1. Whereas the generative models you can actually generate because there's a generative story for sampling things. Moreover, maybe you can even hide some features or not hide, but maybe you have access to some features for an input but not the rest. So you can sample the rest of the features. You can marginalize. You have the full distribution. You can do all sorts of things involving the full distribution. Whereas here, you can do one thing and only one, which is predict. That's the difference. For example, with generative models, you can sum over feature number 1 of P of x, y. Let's say, so this would say this will give you a marginal probability over a certain, maybe only the observation that you have. Maybe you don't see feature number 1. So you can ask what's the probability of what the stuff that I see, and things like that. So you could do all sorts of fancy stuff because you have the full probability. Which is why some people tend to like generative models because they give you a more powerful tool, a more powerful set of tools. The problem is you are learning a lot more, which means you need a lot more data to get equally good because you're basically learning the full distribution. Does that help?
Yeah.
Are there other questions?
Sorry, okay. So even though they're both linear classifiers, because we're learning all this extra stuff, the BC dimension of naive Bayes would be less than.
Yes, that's right. That's right. Yes. So, yeah, this is something I just said. The generative model tries to characterize the distribution of the inputs. The discriminative model doesn't really care. All right. So now this is a good introduction because I want to compare a discriminative and a generative model that are very, very similar to each other, namely naive Bayes and logistic regression. So let's go to logistic regression. In some sense, logistic regression, different machine learning classes introduce logistic regression in different ways. I choose to introduce it at the end because I think it's a very cool synthesis of pretty much all the ideas we've seen this semester so far. We've seen linear models. We've seen learning as loss minimization. We have seen Bayesian learning, namely the maximum likelihood and maximum a posteriori learning, we've seen the naive-Bayes classifier. And having seen all of these things, the logistic regression classifier is basically from can be connected to each of these things in interesting ways. So let's look at what logistic regression is. I'll show you the connection to naive-Bayes. If time permits, we'll get to the end of how to train a logistic regression classifier. I'll probably skip the content on loss minimization because these are exactly the slides that we saw before. So let's talk about logistic regression. The setting is the usual sort of setting that we see. We are given some training examples. Logistic regression is a binary classifier. We have feature vectors, which are d-dimensional vectors, real valued, and the labels are -1 or 1. When we have an example for this kind, we need to learn a classifier. The output is -1 or 1. Now, instead of predicting the output, what if we care about predicting a probability of the output? In other words, we want to predict the posterior distribution of y given x. That's why it's a discriminative model. We directly want to characterize this distribution. Now, which means we need to learn a function that produces probabilities. Functions that produce probabilities are, probabilities are real numbers between 0 and 1. So we need functions that can produce real numbers between 0 and 1. Which means what we have is a regression problem. The original problem we had was predicting, mapping these features RD in RD to -1 or 1. That was a classification problem. Instead, we have to now find hypothesis spaces that contain real numbers in the output. So we need to produce numbers in the range of 0 to 1. So we have a regression problem. Okay, so we have a regression problem, and we need to predict probabilities. At this point, the questions, it's a wide open field. There are many functions that can produce numbers between 0 and 1. So we need to make a hypothesis-based assumption. So we need to find a set of functions that are, for whatever reason, interesting, that can produce probabilities. This set of functions, it turns out, can be very neatly characterized using the sigmoid function. The hypothesis space for logistic regression, keep in mind, this is a function that produces a probability, is defined in terms of a sigmoid function. That we talk about what a sigmoid function is. So what you do is the logistic regression is completely defined using a weight vector W. There's also a bias, but I'm ignoring the bias. I'm doing the usual thing of hiding the bias here. So there is a weight vector W. When a new example comes in, you take the dot product of W and X, and you get a number, right? You take the number and you transform it with what is called the sigmoid function. The sigmoid function takes anything and returns this thing here, 1 over 1 plus e power minus z. This is a very, very widely used transformation across machine learning. The whole theory of neural networks was built up using based on the sigmoid functions, and we'll encounter this again next week when we come to neural networks. Is the logistic function. So the hypothesis space for logistic regression is the following. It's defined in terms of a certain set of weights, W. Given a new example, you take the dot product of the weights with your features, and you transform it with the sigmoid function, which is 1 over 1 plus e power minus 3. So you get at the end you get a number, and we're going to pretend that that's the probability of y given x. Now, why is this a reasonable choice? We need to think about what's the domain and range of the sigmoid function. The domain is simple. It takes any number. Right? It can take any real number. When the number z goes to infinity, this quantity becomes 1 because this becomes 0, and you get a 1. When z becomes 0, this quantity, the e power minus z, yes?
What did you say with the original range? Did you use the hyperbolic tangent function?
Well, the hyperbolic tangent is from -1 to 1.
Right.
So it's not a probability. It turns out the hyperbolic tangent and the sigmoid function are basically just deterministic transformations of each other. So they are, if you have a hyperbolic tangent, you basically have logistic regression. If you want to plot the sigmoid function, it looks like this. As z increases, you get close to 1. As z decreases, you get close to 0. In fact, sometimes I've seen code where they approximate the sigmoid function as equal to 0 beyond 6. For some reason, 6 is a number beyond which you can't see the difference. And equal to 1 beyond 6 and equal to 0 less than minus 6. You can have it's a function that has this, this sort of a characteristic S shape. That's why it's called that shape, except it's just a scaled version of the same thing. So it goes from -1 to 1. So the one thing that you will do also in your homework, one thing that is something you should be aware of is we will be using gradient-based learning. We need to understand what's the derivative of the sigmoid function. You can take the derivative of the sigmoid with respect to z. And this is just, calculus, I don't know, 1.5 even. You can go through this process, but the nice thing is the derivative of the sigmoid is sigmoid times 1 minus sigmoid. You should be able to step through this and work it out yourself. I'm not going to spend any time on this. So, but the bigger point that I would like you to kind of keep in mind is for logistic regression, we are making a hypothesis-based assumption that when an input comes in, we are taking the dot product with some weights and applying the sigmoid transformation to get what we believe are probabilities. And which probabilities do we believe? According to the model, we say that the probability of y equals 1 given x, and suppose we have learned the w, so given x and w, is sigmoid applied to w transpose x, so it is 1 over 1 plus e power minus w dot x. The probability that y is minus 1 given x and w is just 1 minus the probability that y equals 1. 1 minus this quantity is exactly the same as e power minus w transpose x divided by the same denominator. Now, e power minus w transpose x divided by 1 plus e power minus x is the same as I can multiply throughout by e power w transpose x, so you get 1 divided by 1 plus e power. Right? So, probability of y equals 1 is 1 over 1 plus e power minus w transpose x. Probability of y equals minus 1 is plus w transpose. So, together, you can combine these and you say probability of y given x is 1 over 1 plus e power minus y w transpose x. So this is the logistic model. So given any example x, you can predict the probability of y as 1 over 1 plus e power minus w transpose x. And I say that fast because I've been saying that all the time. But this is the model. The important thing to note is we are directly predicting the probability of y given x. In naive Bayes, we wanted the probability of y given x, but instead we applied the Bayes rule and worked with the likelihoods and the priors. Here we are completely giving up all that, any pretense of playing with the likelihoods and the priors. We say, I care about the probability of the label, and we just get the probability of the label instead of going around my head. Any questions about the logistic model? About the hypothesis space, about what we are doing here?
This is a probability of the label given the input and the weight.
Yes. I put the weights on the given side because in order to compute the probability, we need the weights. So essentially, this is asking what's the probability of the label if you know the input and you also know the weights. We cannot compute the probability without knowing the weights. So we need to assume that learning is done and we have the weights. When we are doing the learning, we will derive the loss function based on as a function of the weights. We will pretend that the weights are unknown and x and y are known. When we are predicting, we will assume that weights are known, x is known, and y is known. Because we need to make a prediction. There was another, yeah.
So essentially, what Bayes and logistic prediction are just predicting probability of
Yes. No, we're not probability of the hypothesis based, we're predicting the probability of the label. In both of these cases. In both cases, we are predicting, given an input, we are constructing the probability of a label. In naive Bayes, we construct the probability of a label by multiplying these two, and we say the probability of a label given x is proportional to the product of the likelihood and the prior. In logistic regression, we say the probability of the label, there's no likelihood and prior, the probability of the label given x is just this quantity, correct? So, yeah, I mean, in both cases, we are predicting the probability of a label given. Yeah.
So having predicted the probability, do we just, to turn this into a classifier, do we just choose the most likely label for?
We apply map prediction, maximum a posteriori. This is our posterior probability. We find the label that has the highest posterior probability. In other words, we find the label that has the highest probability given the input. In fact, that's literally what it is. That's exactly what I have. How do you make a prediction at the end? We can compute the probability. What does it mean to say that a certain label has highest probability? We have only two classes, so the highest would have a probability more than half. So if you want to convert this probability into a prediction rule, what you do is you compute the probability and check with half. Compared to half, if it's more than half, you predict that label. So if probability of y equals 1, if p of y equals 1 given x, I'm going to skip the w when I'm writing it this way. It's greater than or equal to half, then label equals 1. But now let's kind of work with this a bit. So let me erase this here and compute this probability if p of y is 1 conditional x is given to half, then if this quantity is true. But let me expand that out a bit here. What is it? By definition, p of y equals 1 given x is 1 over 1 plus e power minus w x is greater than or equal to half. If this is true, then label equals 1. I'm going to just take the inverse of these things. This means 1 plus e power minus w x is less than or equal to 2. If this is true, then the label is 1. That means e power minus w x is less than or equal to 1. If this is true, the label is 1. I can take log on both sides. That means if minus w transpose x is less than or equal to 0, the label is 1, or the label is 1 if w transpose x is greater than or equal to 0. We start with the whole story, we come back to linear classifiers. Logistic regression is just a linear classifier with a probabilistic kind of antecedent. The prediction with the probabilistic regression is, we don't need to do the whole thing of computing probabilities and taking the exponent because that could be a numerically unstable operation. After learning is done, we just compute the dot product of w and x and look at its sign, and we get the label, and you can sleep better at night knowing that there is a probabilistic meaning to all this. It also gives you a recipe for converting the output of perceptron and SVM into a probability. Just pop it into a sigmoid function. Yes.
Well, I imagine maybe there are other functions other than the sigmoid that might work for us as well.
Yes.
Do those work better for certain distributions, or is it?
So it turns out this works pretty well because of what I just derived. Because it corresponds directly to linear classifiers, and there's a whole. This is a pretty. We know that linear classifiers are a rich family of values and all that stuff. Yeah.
Given the same initial conditions, will perceptron and logistic regression come up with different weights for the same data?
Quite possibly. Quite possibly. I want you to revisit the lectures on learning at loss minimization because it turns out the perceptron and logistic regression minimize different loss functions. The goal of learning is different. In both cases, we want to find the best linear classifier. How we define best is different, so we might end up with slightly different things. So they are essentially solving different problems to arrive at to search over the same hypothesis.
Given that, will they come up with different answers?
In practice, I have to say, in most cases, in many cases, I have hardly ever found a difference between logistic regression that is well with proper choice of hyperparameters, SVM with proper choice of hyperparameters, or average perceptron with proper choice of hyperparameters. They tend to be roughly equivalent, and the one that I use tends to be the one that I have the code lying around. It's mostly a practical thing. I don't. Hopefully, you will come to the same conclusion with your projects and your the current homework, where you will actually compare logistic regression against. In practice, I have found that some people tend to be very religious about these differences, but it hardly makes a difference unless you want to kind of build a story around your model. If you want a probability, if you want well-calibrated probabilities, you're probably better off choosing logistic regression. If you want to say something about the margin, you probably want to use and things like that. So there is, if you want the origin story to stick, then you go with that. Otherwise, you just use one. I saw half a hand somewhere here, but yeah.
So it seems like the next thing you want to do is get this to binary classification. But can we still arrive at that same equation of UI?
So it turns out, okay, this is a very good question. In fact, it's a question I've tried avoiding for the entire semester. It turns out that extending binary to multi-class was an open question for a while, but there are very, very well understood generalizations of these things. I can give you a paper recommendation if you want, but the general idea is that there is a very neat extension of all these binary models to the multi-class, where all the properties I described come to. If you extend binary SVM to multi-class, you get, not surprisingly, the multi-class SVM. That's the name. If you extend or beyond multi-class, let's say you have multiple correlated predictions that you need to predict. If you extend logistic regression to the multi-class setting, you get what is called the I can't remember the name, poly something multi-class, but more generally, you get a conditional random field. You may have heard of conditional random fields. Conditional random fields are the extension of logistic regression to multi-class setting. Now, they tend to be linear as well. If you squint and kind of define linear in a certain way, because you can't just have two sides. Like a hyperplane cuts the space into two parts, you get positive and negative. You need to define an equivalent extension of linear for multi-class, and you get that. We can talk offline if you want. This is something that I spent a lot of time thinking about, so I can keep talking about it. So that's one way of doing it, where you kind of partition the classes into groups, but then you are naturally introducing a certain structure over the part, saying that label 1 is closer to label 3 than label 7. Maybe that's not right. Just as one last thing I want to say about this is this was a paper from 2010, as recent as 2010. This stuff has been around forever, and it still happens to be one of my favorite papers. So the title of the paper is From Binary to Multi-Class. We can talk offline if you want. As you can see, this is stuff I really find exciting. Right. So we have logistic regression, we have a linear model. I want to now spend a few minutes talking about why I arranged the lecture so that I first talk about naive Bayes, then talk about discriminative and generative, and introduce logistic regression, because logistic regression has a very tight connection to naive Bayes. Naive Bayes was, I mentioned it without proof, but naive Bayes is a linear classifier. And what I mean by that is the ratio of the posteriors is a linear function. If I take the ratio of y equals -1 given x divided by q, y equals +1 divided by x, and take the log of that, that's a linear function. Now, I'm writing naive Bayes here as if it natively computed the posterior probabilities, but keep in mind that it does not know the posterior probabilities by itself. It computes it using the likelihood and priors, generative model. So in the naive Bayes classifier, this ratio is linear. But we also know that these two quantities are not really independent of each other. So the denominator and the numerator should add up to 1 because they are both probabilities over the same thing. P of y equals 1 or P of y equals minus. So I can get rid of one of these things. Let's say we today we only keep this. Let's say we eliminate P of y equals plus 1. So you say log. I'm going to just for the what I'm going to write here is for shorthand. I'm going to write this quantity as P and this quantity that you don't need to write it because it distributes. So P divided by 1 minus P is W1 for that. I can take E power on both sides, so you get P divided by 1 minus P is E power X. And now I can multiply the thing with P equals P times power X. And I can keep the P side terms on one side, so it's P times 1 plus. Oh, there's no minus. Yeah. W comes with X equals P power. P is P power. Right? So this is really probability of minus given X. It's exactly the same thing we had for logistic regression. It means the probability of plus given X is 1 minus this. Probability of plus given X is 1 divided by 1. So what happens here is the decision boundary. So the logistic regression model says, I don't care about all this generative Stodian stuff. I know that the probability of plus given X is this function. Let me directly characterize it. Naive Bayes says, I don't care about your decision boundary. I want to get the priors and the likelihood. And in the process, it ends up with the same decision rule. So the posterior probabilities that the naive Bayes classifier and the logistic regression classifier explore take the same form, take the same functional form. In both cases, this is the posterior probability with the appropriate choice of the W's. It just so happens that the naive Bayes classifier gets to the same posterior in a different way. And the logistic regression directly gets to this posterior distribution. They compute the same posterior distribution, but they may not be equally expressed because the naive Bayes classifier uses its capacity to do other things. The naive Bayes classifier is a generative model. Logistic regression is a discriminative model, and both these models are characterizing the same class of posterior functions, which is very interesting. And in fact, these kinds of things, two functions are called a generative discriminative pair. This is like the classic example of such a pair. In fact, I'm going to have to struggle to, oh yeah, there are other examples of this too, but this is the one that is most commonly used when people want to compare generative and discriminative models. If you want a paper recommendation, there's a very, very well done work from Andrew Ng from I think 2002 or 3, which compares generative and discriminative models by explicitly studying the properties of these two, by seeing which of these work better in different regimes. When you have more data, is it better to have a discriminative or generative? When you have less data,
So will these two models get literally the same answer if they have the same training data?
No.
Or is it they're trying to maximize something?
They will get the same answer if they have the same W's.
Okay.
These two different learning algorithms will might end up at different probabilities, but they are exploring the same class of functions.
Okay.
Yes. Yeah.
Maybe it's not that I'm machine, right? The probability is limited by the resolution.
Mm-hmm. Yep. Well, at this point, we don't have a deep network. We just have a one depth of one. But I'm going to kind of cut you off because I know your question, and the answer is yes. The resolution of the machine becomes extremely important. With these classes of models, it's very rare that we ever work with probabilities. We always work with log probabilities. And as a result, if you work with log probabilities, you get large numbers. In logistic regression, you never ever keep the weight, you never keep the probabilities, you just work at the W's. Because with the W's, you can make a prediction, correct? With naive Bayes, you don't work with the probabilities, you just have the log likelihoods and the log priors, and those are larger numbers. But the deeper question you're asking is extremely important. As you keep multiplying probabilities around, you should start worrying about hitting zeros and underflows because our computers can only represent so many bits. And it's very, especially when you start multiplying small numbers, things get very small. Yes. All right. Now, there are 7 minutes left. I'm going to at least try to do maximum likelihood estimation for logistic regression. Let's see how far that goes. So, what we have seen so far is what a logistic and we are trying to characterize the probability of the label given the input. It has interesting connections to naive Bayes. The only thing that's left is how to train the model. And I'm going to show you half the story, and the other half you're going to do in your homework. So the usual setup for maximum likelihood estimation is we have some data set and we want to find a classifier that maximizes the likelihood of having generated the data. So we want a set of, the classifier is completely defined by the weights. So if I give you the weights, you learn the classifier. So our goal is to find a W such that the likelihood of the data S is maximized. So we know that our examples xi and yi are all independent. So how do we write down the likelihood? What can we say about P of S given the weights? If we know that all the examples are IID. Speak up.
So given we write them as product of all the product of probabilities given W.
Right. You write this as a massive product over all the examples of some probabilities or something. So because all our examples are independent, S is really the shorthand for this entire set. So we just have this big probability and we have IID assumption, so we just break it up. Okay? So that's what I've done. So we want to maximize the probability or the likelihood of the data, and we want to find the W that maximizes it. That's exactly the same as finding the W that maximizes this product because we have IID. And next thing is the standard thing that we've been doing all the while. We never work with likelihoods. We always work with log likelihoods. So we can take the log of this quantity. So solving this problem is identical to maximizing the sum of the log likelihood, the log likelihood of the data. Right? I've just taken log of this thing and the sum product becomes sum. Okay? So now we can actually start plugging in things. We know that P of y given x is the sigmoid of yw transpose x, which is that thing here. So we can simplify the log. So we can take log P of y given x, w is log of that thing here, which is simply the negative log of 1 plus. Right? So I just took the log of that thing here, so we can substitute this quantity in here directly. So solving the problem on top is equivalent to solving the sum of all the log of 1 plus e power minus yw transpose x. Our goal is to keep in mind that our goal is to maximize the likelihood. So our goal is to, the goal of maximum likelihood training is finding a discriminative classifier that maximizes the likelihood. And just with two steps of algebra, we managed to get an expression of this kind here. This must look somewhat familiar, or at least somewhat, it must look like something we have seen before. What we are doing is saying we are setting up a certain loss function. We're setting up a certain loss function called the log loss, or the logistic loss. It usually does not have the minus here. And we're trying to find the weights that maximize the quantity, the total logistic loss. Yeah.
Do we turn this into a minimization by picking out the negative? And
That's exactly right. We are going to turn it into a minimization, but,
and then gradient descent.
and then gradient descent. That's what you're going to do in your homework. And then stochastic gradient descent. All you have to do is just take the derivative of this thing with W, and the whole thing works through. So what we have is we care about solving a maximum likelihood problem. We end up with a function that's like basically a loss minimization thing. But conspicuously absent here is a regularizer. In the loss minimization world, we want in SVM, for example, we had the regularizer plus some loss. Here, there's no regularizer. How do we bring in a regularizer? And the answer is we don't call it a regularizer if you are in the probabilistic world. We call it a prior. A prior is something that tells you here are the kinds of here are properties in the weights that I like before I see any data. One interesting prior, and once you introduce a prior, you're no longer doing maximum likelihood estimation, you're doing maximum posteriori. Once you introduce a prior, we can kind of write down the posterior probability. So one commonly used prior for logistic regression is the following. Pretend that every weight comes from a certain normal distribution centered at 0 and with a standard deviation sigma. So the prior probability of the weight is simply product of over all the weights of this probability, which is just a normal distribution here. Okay, now I can do the whole thing again. So the log, I can do map estimation for logistic regression. I have a minute. It's going to take me 2 minutes. So, which of hands? Should I go for it?
Yes.
Okay, let's do it. That will also set us up nicely for the next lecture. So we have the prior of W, which is just the norm product over all the normal distribution. We're going to go through the whole procedure again, but very, very quickly, because it's going to be, most of it is just copy paste from the other thing. So our goal is map estimation, and we want to maximize this quantity here, probability of the posterior probability of the weights given the data. This is the first instance of map estimation that we are saying. But the posterior probability is simply the product of the likelihood times the prior. The likelihood is what we saw before. The prior is what we have here. We're just going to copy everything down and put it in one place. So we want to maximize W given S, which is the same as maximizing the product of these two things, the likelihood and the prior. We will never ever work with probabilities. We work with log probabilities. So maximizing the sum of the log likelihood plus the log prior. We just did the whole thing with the log likelihood. So this is exactly the same as this. The shaded thing is showing you a history of that. So let's just focus on the prior. Log of the prior, I can literally take the log of that quantity there. It's basically some ugly stuff times e power minus w squared, which is just if you take the log of everything, you get sum over w squared plus terms that don't depend on w. Let's dim out everything that's irrelevant. We want to maximize over w sum of the log losses plus sum of the squares of the weights. That's literally the squared norm of w. Right? So the logistic regression with map estimation is simply maximizing this quantity here. Maximizing the sum of the log loss plus, we're not calling it a regularizer. We are a Bayesian today. So we have a prior weight. We have a normal distribution. And when we were working with SVMs, the same thing has a history of the margin and all that stuff. But those things don't exist. Today we are Bayesians. So That's the end of the story. Maximizing is the same as minimizing, so we can basically get a single optimization problem, and that will be the end of today's lecture. We are minimizing the sum of the loss plus quantity here. I'll pick this up in the next lecture. Oh, I have office hours at 4 o'clock.